Question 4 from the 2023 Advanced Higher Physics Examination from the SQA. In planning for a crewed mission to Mars, scientists have designed an Earth return vehicle, given the initials ERV. When the crew is on the surface of Mars, the ERV will be in a circular orbit around Mars at an altitude of 2.5 times 10 to the power 5 metres above the surface. And for 2 marks, we're asked to show that the gravitational potential at this altitude is given by minus 1.18 times 10 to the power 7 joules per kilogram. Well, we know this important fact from the Advanced Higher is that gravitational potential V is defined as the amount of work done per unit mass, bringing it from infinity to a particular point R from the planet's centre. And it's given by this relationship here. We know the potential V is equal to the universal gravitational constant G times the mass and divided by the mass of the planet divided by the radius where in fact this object is placed from the centre. Picture shown here shows you Mars, and it shows you the satellite in this position here, or the MRV as it's called, or the ERV. Now the gravitational potential means that ERV there has been taken from infinity up to there, and we must find out what its potential is at that particular point. Now we know what G is from the data sheet. G is that value there. We know that the radius of Mars is going to be that value there. This is all just given in the question, in the relationship sheet and in the question. And the mass of Mars is going to be 6.42 times 10 to the power 23. And we know that the altitude of the ERV is going to be 2.5 times 10 to the power 5 metres above the surface. And it's very important to note that this R here is actually going to be the radius of Mars plus the altitude of the ERV. That's the definition of what R is here. So all we have to do is plug those numbers into the equation, and we get that the potential is going to be minus 6.67 times 10 to the power minus 11. And I'll just throw a wee 11 in there for that one. Minus 11 times 6.42 times 10 to the power 23 divided by, of course, the combined distances of RM plus RA. Now we do that in our calculator, we end up with the value which the question has asked us to find. The potential at that point of the ERV is going to be minus 1.18 times 10 to the power 7 joules per kilogram. But the big question for us in Advanced Higher is, why is the potential minus here? The potential is minus because really the work done per unit mass, we haven't done work per unit mass because the gravitational field strength of this planet is actually attractive, is bringing in the spacecraft without the need for us to do work on it. And that's why we get the potential to be minus 1.18 times 10 to the power 7 joules per kilogram. Question 4, continued part B. The ERV will then move into a higher circular orbit. The gravitational potential at the higher orbit is minus 1.10 times 10 to the power 7 joules per kilogram. And the ERV will have a mass of 4.3 times 10 to the power 3 kilograms. And for 4 marks, we're asked to determine the change in the gravitational potential energy of the ERV when it is moved from the lower orbit into the higher one. So here we have the situation here, a picture of it. We have the orbits round Mars, and that's the ERV in the first orbit, where it's got a potential of minus 1.18 times 10 to the power 7 joules per kilogram. And it's going to move up to this orbit up here, and we've got to find a change in the potential energy of that situation. Now notice we're talking about potential energy this time, not potential, but we start off by working out the differences in potential. Remember, potential energy is just really potential times the mass. So what we're trying to find out here is the difference in potential between these orbits here, from that one and that one. So we start off by saying what's the change in the potential, delta V, and it's got to be simply equal to the potential of this orbit, minus 1.10 times 10 to the power 7. I'll leave out the units for the moment. Take away, and be careful, we're taking away a minus 1.18 times 10 to the power 7. Minus 1.18 times 10 to the power 7. And it's going to be joules per kilogram. So when we work that out, remember the minus, take away a minus is going to give us a plus. So we're going to have minus 1.10 times 10 to the power 7 plus 1.18 times 10 to the power 7. And we work that out in our calculators, we get 0.08 times 10 to the power 7. And our units, since it's still potential, is joules per kilogram. So the actual potential energy difference, which we'll call delta E, is just really equal to the mass multiplied by this potential. Remember, the potential energy is the mass times the potential. So we know the mass of the ERV, it's going to be 4.3 times 10 to the power 3 kilograms. And we're going to multiply it by our delta V, our change in potential, which worked out was 0.08 times 10 to the power 7. And it's going to be joules per kilogram. So if we do that, we get an answer of the following. We get 3.44 in our calculator times 10 to the power 9 joules. So that's the change in potential energy when the actual ERV goes from this orbit to that one there, a higher orbit. Question 4, continued part C. Another spacecraft, the Mars Ascent Vehicle MAV, will transport crew and cargo from the surface of Mars to the ERV. For 3 marks for part 4CI, we've got to calculate the escape velocity from the surface of Mars. Well, let's see how we do that then. First of all, a definition of the escape velocity. The escape velocity is defined as the minimum velocity required for an object to leave the planet's gravitational field and reach infinity with zero kinetic energy. And also the potential energy at infinity has got to be equal to 0 as well. Now let's take a note of this then. There's the planet Mars. We know it's going to have a radius r. That's going to radius r there like that. And that's the object on it, which is going to have a small mass, radius r of the planet. And the planet itself is going to have a mass of capital M. Now, if we go and take that object to infinity, let's imagine represented by that line there, then what we can say is that at infinity, there's going to be no kinetic energy, there's going to be no potential energy, so the sum of the potential energy, EP, plus the kinetic energy, EK, will be equal to 0. Now, due to conservation of energy, if we go to the surface of that planet Mars, then the object of small mass m, its potential energy plus its kinetic energy should be exactly the same, equal to 0. Now, we know a value or expression for the potential energy of an object, and the potential energy EP is going to equal to minus G capital M small m over r. That's the potential energy of an object of mass small m, distance r from the centre of a large mass m, and G is universal gravitational constant. We also know EK. That's quite easy to do. EK is 1/2 times the mass times the speed squared. So if EP plus EK equal to 0, we've got this relationship here, minus G capital M small m over r, plus a 1/2 m v squared, and that should equal to 0. We can rearrange now. We can say that 1/2 mv squared, to keep that on this side, take the minus G capital M small m divided by r over to the other side, and we have that. And you can see we've got 2 m's on each side, so we can cancel those out. And we can multiply both sides by 2, and we're left with just v squared is equal to twice the gravitational field strength times the mass of the planet divided by r. And our last move then is to find the value for v by taking the square root of that expression, 2g capital M over r. So we've got all the particular data we need to know for this particular problem. We know what the universal gravitational constant is, we know the radius of Mars, and we know the mass of Mars. So from those 3 constants, we can calculate then the escape velocity to escape from that planet. So all we have to do is plug in the numbers. We just go up here and say v is equal to the square root, and the number is going to be 2 times g, which is 6.67, times 10 to minus 11, we'll just put a bracket around that, multiplied by the mass of the planet, which is 6.42 times 10 to the power 23. Okay, that's the top one done. And we're dividing that by the value for the radius of the planet r, which is 3.39 times 10 to the power 6 of a metre. We do that in our calculator and we end up with an answer of 5,026 metres per second. That's the escape velocity of an object to escape the gravitational field of Mars. Part 2. The MAV will dock with the ERV in the higher circular orbit at an altitude of 5 times 10 to the power 5 metres above the surface of Mars. For 1 mark, we're asked to explain why the MAV does not have to attain the escape velocity calculated in the previous part of the question. Now, an interesting look about this is to imagine the planet Mars is actually sitting at the bottom of a potential well, a gravitational potential well. That's how physicists see this. And there's the MRV, the MAV there like that. It's sitting in at that orbit, which has got a certain potential. Now, if I give it the escape velocity, it's going to go up to here, which is going to be what we call the escape velocity, which is going to take it away from the planet completely. It's going to have no kinetic energy. It's going to have no potential energy. But we're not going to escape the gravitational field of the planet. We're only going from one orbit up to the next, so it won't require the escape velocity. It might require a bigger velocity to take it from the lower potential to the higher potential. So the answer for just simply 1 mark is it doesn't need to have as much as the escape velocity, but the escape velocity will take it to the zero of potential, the place where we call it's escaped completely the influence, the gravitational field of Mars. And it just needs a certain amount of velocity to lift it to the next orbit. Question 4, part C, part 3. Calculate the tangential speed of the ERV in this orbit. Well, let's take a look at a picture of what's happening. We can drag our picture over here like this, and we have the following. We have the Mars, mass m. We have a small mass, which represents the ERV of value small m. We've got its tangential speed, and it's got a height above the surface of h, and of course we've got the radius of the planet r there like that. So it's got a centripetal force acting on it to keep it in an orbit, and the centripetal force, which we'll call Fc, is equal to simply mv squared divided by r. Now that centripetal force arises from the gravitational force, and the gravitational force Fg is equal to capital G, the universal gravitational constant, times the mass of the planet Mars times the mass of the ERV divided by r squared. And of course, remember, both these r's here is the sum of the lengths from the radius of Mars plus the altitude height h. So we've got to add on r. R really stands for, if I can put it in here, r stands for rm plus the height h. So we have to be very careful when we do that calculation. So let's make sure the two of them are equal. We've got the centripetal force mv squared divided by r should equal g capital M small m over r squared, and we're going to get a cancellation here. You can see that we can cancel m divided by r in both sides, and we're left with an r at the bottom here, the denominator. So we've got v squared is equal to g m over r. So we can go ahead now and work out what the tangential speed is. V, it's just simply going to be the square root of the universal gravitational constant times m divided by r, and remember r this time is also the radius of Mars plus the height which the ERV is at. So be very careful when you do that calculation. So we know the numbers now, we know all the data, and the data is quite simple. We know that g is that value there, we know the mass of Mars is that value, we know the radius of Mars is that value, and we know the height, the altitude of the orbit is going to be that value there. So it's just plug in the numbers and we get the following. We get v is going to be equal to the square root of, and at the top you're going to have 6.67 times 10 to the minus 11, and that's going to be multiplied by the mass of the planet Mars, 6.42, times 10 to the power 23, and that's going to be divided by this value here, which is going to be Rm plus h, which is going to be the radius of Mars, which is going to be 3.39 times 10 to the power 6, and it's going to be plus the altitude of the ERV, which is h, which is 5.0 times 10 to the power 5 meters. So it's a simple calculation to do in your calculator. Just take your time, work it out, and you should have a value of about 3.3 times 10 to the 3, and it's going to be meters per second. And that's going to be the tangential speed of this ERV as it goes into orbit round here like that. V, tangential speed, 3.3 times 10 to the power 3 meters per second. Part 4 suggests a reason why the docking manoeuvre will be easier to carry out at an altitude of 5 times 10 to the power 5 meters rather than an altitude of 2.5 times 10 to the power 5 meters. And it's for 1 mark. Well, quite simple. If we look at this little movie here we have, you can see that if you're in a higher orbit, you're going to go at a much slower tangential speed. The blue dot, or the blue satellite orbiting the Earth there, has got a bigger tangential speed because it's in a lower orbit. So if you go to a higher orbit, your tangential speed is going to become smaller, which gives you a better chance to dock safely with another spacecraft in that orbit. You're not going to be travelling too fast approaching each other. So that's a simple 1 mark response for that then. At lower orbits, you travel much faster, your tangential speed is much faster. At a higher orbit, your tangential speed is slower, therefore you have less chance of collisions with bigger kinetic energy and all that sort of stuff. That's your answer for 1 mark.